If you remember back, we did reflections, we did rotations, we did translations. They were all rigid motions. A dilation is another type of transformation. The dilation, though, does not preserve distance. It makes things larger or smaller. So a dilation is not a rigid motion. The translation, reflection, and rotation, those are your rigid motions. So dilations result in similar figures. That's the big idea. So I got a triangle here. Do you think you could read through this and then figure out the measure of angle F prime and the measure of segment F prime T prime? So let's just draw this figure, triangle CFT. So I don't know, maybe it looks something like this. Here's triangle CFT, angle F is 40. And segment FT has a length of 8. So if I do a dilation of scale factor 2, so I'm going to make the triangle twice as big, and it's going to be centered at vertex C. So maybe our dilated figure, now I'm going to move this down a little bit. Maybe our dilated figure looks something like this. I got to multiply that distance by 2. Got to multiply that distance by 2. Got to multiply that by 2. So my green triangle is going to be triangle C, F prime, T prime. So how big is angle F? Well, the dilation keeps angle measures the same. So angle F prime is 40 degrees. And what's the measure of segment F prime, T prime? F prime, T prime is going to be twice as big. The scale factor is 2. So that's 8 times 2, which is 16. So that's an important thing to notice. Notice that we do 8 times 2 to get 16. And also, if we knew that this figure was 16, the scale factor, just to check that, is going to be the image divided by the original. 16 divided by 8. We're going to come back to that in a moment. So I want you to kind of recognize that. And a moment is here. How about that? So I've got a figure here. I got triangle boy, and then I dilate it centered at point Z to get triangle man. The boy has become a man. And I want to know what a ratio would be that would represent that scale factor. I don't have any numbers, but I can still write out what the ratio would be. Think about what we did before. We said if we're doing a dilation of point B, it's going to go out to point M. So the image is going to be the distance it takes to go from Z to M. The original is going to be how far it goes from Z to B. So one ratio would be the length of ZM to ZB. Likewise, we can keep going the other way. Do you notice that all these points are collinear? Like Z, O, A. A is collinear to Z and O. It's kind of neat. We can also say that ZA to ZO is our relationship, is our ratio. And if you want to go one more time, we can go from ZY to ZN. So again, notice that it's image over the original. So let's switch it up a little bit. Let's suppose that boy is now the image of man. We do a dilation centered at point Z, and our image is smaller. So everything still is going to stay collinear, but this time if we do the image distance, which is Z to B, over the original distance, Z to M, now the ratio is ZB over ZM, or any of the others as well. Just remember that we always go image over the original, and that's what's equal to our scale factor. That's the idea. So as we keep moving, let's apply some of that to a distance on a grid. A lot of dilations are done on grids. This is pretty cool. So I'm given point A and point B. They can make segment AB. And what I want to do is I want to dilate it by a scale factor of 3, and the center is going to be at point D. So let's think about what that does. So that means our scale factor is 3, so I'm tripling the distance. So notice to go from D to A, I have to go like down 3 and over 1. So that's one length. Well, if I go down another 3 and over another 1, that's a second length. If I go down 3 and over another 1, that's a third length. So check out this point down here being A prime. Notice point A prime is 3 times as far away from D as point A is. And likewise, let's do the same thing for B. It looks like I got to go down 4 and over 2. Let me go down 4, another 2. So that point would be twice as far away. Down 4, another 2. There's 3 times as far. So here's point B prime. And what does it say to do? Graph segment A prime, B prime? There we go. There's the segment A prime, B prime. And can you see the dilation of the triangles here? Did you notice? Oh, I'm going to hold off on that. All good things to those who wait. Let's keep rocking. Let's now go the other way. Can we describe a transformation? So in this case, notice that we go from A out to A prime. So think of this as like the image getting larger or the original getting smaller. It's all going to shrink down to one spot. Where is that one spot? Well, if I keep going from A prime down to A, if I go from B prime down to B, if I go from C prime down to C, can you tell that everything shrinks down through the origin? So this is a dilation. Dilations need a center. Dilation center at 0, 0. And they need a scale factor. So notice the distance from the origin to A, and then the distance from the origin out to A prime is twice as far. So we'll say centered at 0, 0. This is a dilation of 2. Because A prime, the distance from origin to, say, A prime, equals 2 times the origin to point A. And the same would be true from the origin to B and to B prime, and from C to C prime. Pretty neat. Okay, this is what I wanted to get back to, check out the dilation from before. So notice that when we dilated point A, centered at D, it just kind of went like further down the line. So it just kept moving that point down that dilation. Same with B. But check out what's going on here with segment AB and segment A prime, B prime. Here's a very, very powerful thing. If I look at the slope from A to B, I'm going down 1 over 3. So the slope of AB is negative 1/3. And if I take a look at the slope of A prime, B prime, it looks like I go down 3 and over 1, 2, 3, 4, 5, 6, 7, 8, 9. Down 3 over 9. The slope of its image is negative 3/9, which you guessed it, is negative 1/3. So what's really neat is the dilation created a parallel situation. But notice that it took segment AB and moved it parallel, but it took segment DA and just kind of stretched it out. So the line that contains DA also contains A prime. That's the idea of that collinearity we talked about before.
Could somebody please come and unlock the office door?
Uh-oh, office door is unlocked. So that's a big idea here. The big idea is that a dilation that takes a line that doesn't pass through the center to a parallel line. And it leaves a line that passes through the center unchanged. So let's talk about what that means real quick. What that means is if I take my center point, and I'm going to take 2 points that are on that line. See how that line passes through the center? These 2 lines pass through the center line, let's call it line L and line M. So it just takes points that are on that line and moves them further down. So if this is point A and that's point B, maybe A prime just goes a little bit further down, as does B prime. But the line that does not pass through the center gets moved to a parallel line. That's the idea here. So how do we play with that? Well, here's the equation of a line. The line is y equals 2x plus 3. And we're going to dilate it by a scale factor of 2, and it's going to be centered at the origin. That's the center of our dilation. Where does the line go? Well, the first thing I'm going to ask myself is this point on the line. How do you check? You plug it in. Let's see. If I plug in 0 for x and 0 for y, I get 0 equals 2 times 0 plus 3. That's false because 2 times 0 is 0. So 0 does not equal 3. So 0, 0 is not on the line. So that means that it gets dilated and it moves to a parallel line. Remember, parallel lines have the same slope. So therefore, the equation of my new line is going to be y equals, let's see, the slope is 2. So it's 2x plus something. Well, what's that y-intercept going to be? Well, here's what a line of like what y equals 2x plus 3 might look like. Let's say that is the y-intercept of 3. Well, the distance from the origin is doubled. So it's going to go up twice as far, which is going to be up at 6. So what goes in that question mark? That question mark becomes a 6. So the equation for the line is going to be y equals 2x plus 6. And again, that goes with that idea that if the point's not on the line, the dilation goes to a parallel line. Parallel lines have the same slope. We just got to change our y-intercept. Let's try one more. So the equation of this line is 4x minus 3y equals 6. We're going to dilate it by a scale factor of 3. Let's check. Is 0 negative 2 on 4x minus 3y equals 6? Let's see. If I plug in 0 for x, I get 4 times 0. If I plug in negative 2 for y, is that statement true? It is, because negative 3 times negative 2 is a positive 6. So guess what? Since the point is on the line is unchanged. So what's the equation of the image? It's the same equation. It's just 4x minus 3y equals 6. So we hit a lot of stuff with dilations today. Here's things you should be able to do. You should be able to determine an equation for a line if the point is on it or if it's not on it. You should also be able to understand this conjecture. That's the last two examples there. Maybe you can go on a grid and you can determine a transformation. You can describe that dilation. Or maybe you can dilate points that are on a grid. Maybe you can find the scale factor as well. A lot of good things here today, my friends. You need some practice.